Hello everyone, welcome back to ECE350, lecture number 3. Today we're going to talk about time domain and phasor domain. So what is a domain transformation? It's basically a mathematical process that converts a set of variables from their domain into a corresponding set of variables in other domain. So how is it done? In like phasor analysis techniques, you from time domain to phasor domain, it basically is equivalent but not the same variables, right? So when you go to in phasor domain, you lose your frequency component, you lose your time component of the time domain signal. But if you want to come back to the time domain signal, you need to know what the frequency of your signal. All right, that's how it is transferred from one domain to another domain. So how is done? So this is a time domain signal right here. So if I want to go to phasor domain, I'm gonna replace this with this equation over here, right? And we're gonna take the real part of it. We're gonna take the real part of it. That is your I would what is a phasor domain signal, right? So what that means. So if I use this equation over here, Euler's identity equation, then if I convert with this equation here, I have this, right? So now if I take the real part of it, that only this part, right? That's only this part side. From the real part over here, I'm going to take only the angle, not the time component, right? So that is your phasor domain. So for the real part, I'm going to take only the angle, phase angle reference, not the time domain. I'm going to leave the time information out. That's your phasor counterpart. So that phasor counterpart only involves this right here. So from this time domain signal over here, the phasor domain only, that's part of it. The time domain over here, there's no angle is 0, so the angle is 0 over here. And for this one here, for the time domain, phasor domain, I will take this and the angle. So right here. So that's how it works, right? So if I put angle is negative 90 degree, that will be negative 90 over here. That is the your what do you call it, phasor domain from time domain. And there's a big chart over here, how it goes from one side to another side. To review that, and how does it apply to the your circuit solution, right? So time domain over here, phasor domain over here. Time domain be equal to IR, and your phasor domain be equal to IR. So R is a real component; it's not going to change anything. I is time domain over here. In the phasor domain, I'm going to take the magnitude and the angle, right? So magnitude and angle, that's your phasor domain. Can you see that? And also for inductor, so you have your VL is L di dt. So this is the I here, and your VL would be L di dt. So L over here, if you take the derivative of I, if you go back over here, you can see from the chart, if you take the derivative, that's right here. So j omega x, so over here is j omega L and IL. That's your VL over here. So if you're trying to find ZL, which is the inductive impedance, is j omega L. So ZL or XL is j omega L, right? Then for capacitance, I equal to C dV dt. If I use the same equation over there, your IC would be what? J omega C VC. Then if you try to find ZC, VC by IC is 1 over J omega C, or you can see XC would be 1 over J omega C, or it's negative J omega C, right? So that is the three fundamental things over here. R is R. So R is R, this real component, and XL is J omega L, and XC is negative J over omega C. So if you have a RL circuit, if you have an RC circuit over here, so if you're trying to find the current in phasor domain, so your impedance would be R is R, negative J omega c, right? Then your current would be voltage over G, and that is Vs over R negative J omega C, right? Then if you uh, that's what is showing over here. If an R, then RL. So for this circuit over here, your RL. So the Z would be R plus J omega L, right? Then your current would be Vs over R plus J omega L. So once you get the current, then you can go into time domain. We're going to do this problem in the class to show you how to go from time domain to frequency domain, time domain to phasor domain, and phasor domain time domain once you have the solution. It's always recommended to solve your circuit problem in the phasor domain. It's easy to solve. Then you can go back to time domain as you know the frequency. All right, and you're going to do this problem in the class, and there's another chart over here. And again, there's the fundamental things about how to go back and forth from the time domain to phasor domains. So let me give you an example over here. Let's say your current in phasor domain is 10 negative 30 degree. Then in time domain, it would be 10 cosine omega t negative 30 degree. Right? See how easy it is. So if you know the frequency, you can just complete the equation. Another tag brief is a photovoltaics. You all know that photovoltaics is a very interesting technology. And how does it work? Photovoltaics effect was discovered by Albert Einstein. How it works? So in photovoltaic technology, you have two things. You have N-type semiconductor here. You have P-type semiconductor here. You know how to make them. You make them with the doping, right? So when your photon with light hits the N-type and P-type semiconductor, so it's absorbed, and some of them also reflected and goes to the next level here. What it happens at the junction over here is builds an electric field in the junction. That electric field is strong enough to separate electron to this side. So this side gets a lot of electron, right? And this side gets a lot of holes. So now this one has extra electron on this side here. There's an extra hole on this side here. So if you connect them through loads, then all the electrons comes from this side to this way, and that means your current goes this way. That's what happens. So light keeps shining. They're generating more and more electrons and hole separation at the junction. Then is continuously supplying current to the load. So that's what's showing over here. So light's coming in, and at the junction over here, you produce enough electric field to separate electron and proton. Then excess electron goes through outside load and come back to the P side to recombine, and that process continues as long as your light is shining. All right, and from the single cell over here, you can make a PV module. Each of the cell normally produce 0.5 volts and around 2 amps. That's what a cell produce. So if you can combine the series and parallel combination of that, you can make a PV module like whatever voltage you want. And from PV module, you can make a PV array to have bigger voltage and bigger, larger capacity of wattage. And from there, you can make a power plant. All right. So at home, if you look at that, you have PV array here. You have a DC-AC converter. Then so that DC also can go to the storage, charging the storage, and also get it from there if your light is not shining. Then you have AC. AC goes to either can go to the grid or can go to the home for your household equipment. All right, that's all. This is the basically a collection of all the equations we have, and we're going to see you in the class and to solve some problem.